So we have a pitcher of buttermilk initially at 25 degrees Celsius is to be cooled by setting it on the front porch where the temperature is 0 degrees Celsius. Suppose that the temperature of the buttermilk has dropped to 15 degrees Celsius after 20 minutes. When will it be at 5 degrees Celsius? Okay, so in order to solve this, we need to use Newton's law of cooling. So that's d of capital T divided by d of lowercase t is equal to negative k times the quantity a minus t. So k here is a constant. Now because we're looking at cooling it on the front porch, the temperature is 0 degrees Celsius. And so capital A is the ambient temperature, and that's going to be 0 degrees. So we can substitute that in and get a d of capital T divided by t of lowercase t is equal to k times capital T. And then from there we can divide both sides by t and multiply both sides by dt. So now we have a separable differential equation where we can integrate both sides, get ln of capital T equals kt plus c. Now we're going to do e to both sides. So in other words, e raised to the power. So e to ln of t would just give me t. And then we have e to the kt plus c. Now I can split this up, this e to the kt plus c as e to the kt times e to the c. And so e to the c is just going to be some constant. And I'm just going to call it c1. Now we're given the initial temperature is 25 degrees Celsius of the buttermilk. So that's T of 0 is 25. We can plug it into the previous equation that we had. So T of 0 is the constant times e to the k times 0. And that temperature is going to be 25 degrees Celsius. Well, the exponent here is 0. E to the 0 is 1. And so we have C1 equals 25. So far, my equation, capital T, is equal to 25 times e to the kt. What's left for me to find is lowercase k here. And so I'm going to have to use another fact. I'm looking for, or rather, suppose that the temperature of the buttermilk has dropped to 15 degrees Celsius after 20 minutes. So when T is 20, the temperature is 15 degrees. So that's this point. Plug in 20 for lowercase t and then 15 for capital T. Divide both sides by 25. Take the natural log. We have 20k equals ln of 3/5. So k is 1 over 20 times ln of 3/5. So now we have the equation for temperature. It's 25 times e raised to the 1 over 20 times ln of 3/5 times t. The question asked, when will it be at 5 degrees Celsius? So the capital T is the temperature. We're going to set that equal to 5 degrees Celsius and solve for time. First, divide both sides by 25 and then take the natural log of both sides. But actually, before we do that, what I'm going to do instead is rewrite this, because what I want to take advantage of is the fact that e to the ln of x is equal to x. So why don't I rewrite this? The 1 over 20, well, I guess I'm using this property. The constant in front is the exponent of what's inside the natural log. So the 1 over 20 is going to be the exponent of 3/5, and the same thing is t. So now I have it as e to the ln of x, where x is equal to 3/5 raised to the 1 over 20t. So what happens is e cancels, and you're going to be left with 3/5 raised to the 1 over 20 times t. Okay, now I'm going to take the natural log of both sides because I want to bring down the 1 over 20 times t. And all I have to do is solve for t. Well, I can multiply both sides by 20 and divide by ln of 3/5. And that's going to give me t is about 63.0 minutes. And that's my answer.